All right, so chapter 2 has 3 sections. We're going to start the first one today. And they're all going to center around this idea of logic and using logical arguments. You're going to have very little in terms of numerical calculations in this section. So if you don't have your calculator, you're in luck. You probably aren't going to need it for the next several sections, okay? So we're going to take a look in this section at something, the title is actually called Reasoning and Logic. And we need a little bit of vocabulary to get started. The first word we're going to look at is the word statement. A statement is a sentence that is either true or false. And I want to give you both an example and a non-example. So an example of a statement would be, I ate eggs for breakfast. That is either true or false. I can't sort of kind of halfway eat an egg for breakfast. I either did or I didn't. Okay? So, and in fact I did, just in case you're curious. I did eat eggs for breakfast, yeah. So this is a statement because I can actually say yes, it's true or no, it's false. A non-example, something that would be considered not an example of a statement, would be something like this. What did I eat for breakfast? This would not have a true or a false connotation to it. It doesn't even make any sense to say, is that true or false? Because it's a question. It's not a statement. Another type of non-example would be something that's a command. Eat your breakfast, right? Where you're telling somebody to do something. That's not a true or a false statement either, okay? All right, the negation, or a negation, is the logical opposite of a statement. If a statement is written P, then a negation is written with a tilde, and then that same thing. So tilde P. Logical opposite. So you kind of might feel like, oh, it's kind of like putting a minus sign on something. And you can kind of think of it that way. We're trying to take what is said and take the exact opposite of that statement. Now, sometimes it's easy and sometimes it's not so easy. With my example above, it's pretty easy. So the negation of that above, my above statement, I only have one statement up there, would be what? What would be the logical opposite of I ate eggs for breakfast? Right. I did not eat eggs for breakfast. Okay. So there's a reason that one was simple to find a negation of. I can put the word not in, it's very smooth, it clearly identified what I was saying in English, right, in our English vocabulary and so forth. But that doesn't always happen. There are some statements that are much more difficult to turn around than just simply putting the word not in. And those are statements that have what are called quantifiers in them. There are 2 types of quantifiers. The first type of quantifier is a universal quantifier. So a universal quantifier refers to each and every element in the set. So it usually has words like these: all, every, no, or none. All the boys in the class ate eggs for breakfast. None of the girls went outside for recess. No one wanted to go swimming today. They're these all-encompassing kind of statements. You know, they're the ones that your parents get mad at you when you say, right? You never, you always, it's that kind of statement. That's what a universal kind of statement is. It applies to everything in some sort of a collection. So, oh, I had an example here. We'll write an example down. I gave you lots of verbal examples, but here's one. All boys This is a nice one. Love their mama. Okay, now we're not saying is it true or is it false, okay? It's simply a statement with a universal quantifier in it, okay? Existential quantifiers refer to one or more elements in a set. So you get words like some, at least one, or there exists. Some boys love their mama. It's different than all, isn't it? Because it almost has the feeling that means also that some don't. It doesn't say that, but you get the feeling that you're sort of leaving an out, right? You're leaving a possibility that there's some boy out there who doesn't by using the word some as opposed to using the word all. So we're going to go with some people like to swim. Again, true, false, that's not the point. It is a statement because it's one or the other, right? It is either true or it's false. But we're not assessing that. We're assessing that it's a statement and that it has the word some or at least one or something like that in it. And the thing to be careful is that creating negations when quantifiers are present takes more care than when they're not. You have to be more careful. So let me show you how we create negations when there are quantifiers present. Here's our first one. All dogs go to heaven. You have to be careful. What does it take for that statement to be false? The very smallest, minimalist, the tiniest thing. What is the smallest thing that could go wrong in this to make this statement false? Say that louder for me. One dog doesn't. Right? That's all it takes. One dog. We don't need all of them. We just need one of them to make the statement false. Agreed? Right? This is when you say to your parents, you always whatever, and they're like, no, remember that one time when? All of a sudden, your statement is false, because it's not always. All it takes is one. So there's a couple of ways we could write that. One way is to say, well, one thing to be aware of is that there's a quantifier, right? The quantifier is causing us problems. And every time we have a quantifier, it will change to the other type of quantifier. So this is what kind? All is what? Universal. So in order to change this statement to give its negation, we have to change the quantifier from universal to existential. So you can write out the word some, you could write the phrase at least one, or you can write the phrase there exists. Any of them are sufficient. Any of them will work. Okay? So I'm going to say at least one because that's the closest to how we were sort of thinking about it. At least one dog. At least one dog what? Wasn't or doesn't or didn't or something, however you phrase it in terms of past or present tense. But at least one dog, I'm going to say does not. There's that word not. You do get it in there. Go to heaven. A negation is the smallest amount of something that makes a statement false. That's what it is. The smallest thing I can change. Part B says, some of my classes this semester are hard. So what is the quantifier here? Some. Some is the quantifier. And is it universal or existential? Existential. So as I'm changing this to the negation, if it's existential now, it needs to become what? Universal. Now, there's two ways to write this. I'm going to write one of them, and if you're thinking of the other one, hold tight and I'll write the other one too. Okay? So one way to change the word some is to change it to the word none. Right? Some of my classes, now I'm going to say none of my classes. Okay? I'll do the other one in a minute, which says all of my classes. That would be the opposite. So none of my classes. None of my classes what? are hard. So I don't ever actually have to change the rest of the statement because I kind of negated the word at the beginning to some degree, right? Some turned into none. I've got a negation to the fact that it says none. So none of my classes this semester are hard. Okay, so this is one way of doing the negation here. Or we could use the word all. All of my classes. And you have to be careful here. So let's see how careful you guys are not knowing what you're supposed to be careful about, because I haven't said yet. None of my classes this semester what? Or it says all of my classes this semester what? All of my classes this semester are hard is like a stronger statement than I started with, right? It's not an opposite.
All of my classes are easy.
Okay?
Or not hard.
Are not hard. That's the one we want. The catch when we're doing something by changing words around, right, if you changed hard to easy, is that somehow you got rid of the middle ground. So this is one where we can actually talk about it in the middle ground. Makes sense to you. Do you have classes that are neither hard nor easy? I always did, right? Just because it's not one doesn't necessarily mean it's the other. There is sort of that in-between gray area that we could be talking about. So be careful. Don't ever change the words that are present. You're welcome to put the words not or to put the words, something like that in there, but you don't want to change the actual words that are being used. And it's a really strong tendency to do that, right? The opposite of tall is short, so let's just use the word short. No, that's not okay. We can say not tall, and that's okay too. So there are two options here. I think one of them is a little bit more natural to read, and it's more like we speak English than the other one. Which one do you feel like is more natural? The top one. I think so too. I think the top one's a little bit more of a natural way to say this, but they're both technically okay. They're both correct. All right? Awesome. Let's take a look at our next topic. Our next topic is something called truth tables. Has anybody taken critical thinking here at OBU? Got a few heads nodding. This is something that's taught in critical thinking as well. We've taught our contemporary math course, a book before that we've used before. Did anybody do contemporary math with me online in this particular group? No. We use a textbook that still does truth tables on the online class when we teach the online class. Truth tables are tables that are used to show all possible true and false patterns for a statement. Okay, so it's an organized way of constructing data, constructing information about logic. So negations in a truth table. So here's the deal. The first thing I want you to draw is kind of like a T-bar. Okay? In the first column, this is going to be my P column, statement P. And what I'm going to compare then in this says negations. So on my second column, I'm going to write tilde P. That's the negation of P. Okay? Yes. Tilde. It's called a tilde, like T-I-L-D-A. If you're looking for it on a computer screen or a computer keyboard, it's in the top left-hand corner usually, underneath one of the second function kind of things or whatever up there. Yeah, tilde. All right, so one of the things that we said about a statement is that it's by necessity either true or false. Those are the only options, right? So a statement is either true, we'll put a T, or false, and we're going to put an F. Please make sure that I can differentiate your T's from your F's because I will not guess. If I can't figure it out, it's wrong. All right? So be careful when you're writing them down. If you're getting a little bit sloppy, sometimes they start to look alike. Now, the whole deal about negations is that they change just enough that it changes the truth value of a statement, right? These two statements being negations, either pair you want to look at, one of them's true, then the other one is automatically false. That's the deal. So if the statement P is true, then the statement tilde P is false. So within a truth table, it becomes very easy to do a negation, a tilde P column, because all I have to do is switch whatever was in the P column. If the P statement was false, then tilde P would be true. So negations inside of a truth table just switch the truth values. Whatever they were before, now they're not. All right, compound statements are statements that are joined with a connective. The connective is one of three things: and, or if then. Those are the three types of connectives. There's an example in your book where they use the word but. But is just another way of saying and. Right? Like, I ate eggs this morning, but I also ate cereal. I didn't, just in case you were curious. But it really means and. It means both things happened. So if you see the word but, just remember but's the same as and in terms of logic statements. There's really three types of connectives: and, or, and if then. And we're going to look at each of those three scenarios and see what happens in terms of truth values when we're looking at those three. So we're going to start out with what's called a conjunction. A conjunction is the word and. It's a connective, it's a compound statement with the connective and. So it's equivalent to an and statement, and it's true if both statements are true. And so if our statements are P and Q, then what goes between them for an and statement is an upside down sort of triangle shape. No bottom of the triangle, it's open, like an angle or a less than sign, whatever. Upside down V, how's that? We'll go with that. V is good. Upside down V. This says P and Q. So let's take a look at what happens in terms of a truth table when that's going on. Now, in terms of your truth table, you've got one column for P and you've got one column for Q because there's two statements that are going on. And you've got a third column that's going to represent the compound statement P and Q. Now, one possibility is that P could be true. But if P is true, it could be that Q is true. Or if P is true, it could be that Q is false. They're just two separate statements. But maybe P is not true at all. Maybe P is false and Q is true. Or maybe P is false and Q is also false. Those are the only options. Only combinations that can exist of those different truth values for two statements. Now that we've sort of run through them, understand that this order is the expected order for every truth table you create. The benefit to that means that no matter what happens next, you can always start a truth table because the first two columns always look the same. True, true, false, false, true, false, true, false. They always look like this. They never change. Now let's talk through, and we're going to do an example. And we're going to try and come up with professors that you know. We've had some changeovers in professors recently, and so I'm going to have to think through who you might know. So I'm going to have the statement, P is the statement, I am a woman. And Q would be the statement, I am a mom. No, that's not what I want. I'm a professor. How about that? No, I know what I want to do. Let's go with this. I teach math. That's even better. I think that's what I normally use. I don't have these written down. I create them at whim when I get to this point. It's good stuff. Okay, so here's the deal. We have 4 mystery guests standing out in the hallway. Pretend, okay? And the first one walks in and it's me. And I walk in and I say, I am a woman and I teach math. And you would say, they're both true. So what I just said was a true statement, right? Definitely a true statement because each individual statement is true. All right. The next person that walks in is, oh my goodness, Dr. Young. That's a good example. I wanted to use Dr. Aiken, but she teaches math, so that doesn't work too. Dr. Young walks in, and she says, I am a woman and I teach math. And you would say, false, because she doesn't teach math, right? She teaches other courses. So this would be false. The next person that walks in is Dr. Bond. I don't know if you know Dr. Bond, but he is right now our only math professor who is a man. So he walks in. He does teach math, but he's a guy, right? He walks in and he says, I am a woman and I teach math. And the first thing you might do is that. You might kind of giggle at him. And you would say, that's false. What a silly statement. And then Dr. Whitlock walks in. And Dr. Whitlock walks in and he says, I'm a woman and I teach math. No, it's not true. It's false. It would be very false. Very, very false. He doesn't do either one. He is not a woman. He is not teaching math, so it's a false statement. Okay? So what I need you to take away from this is that and statements are only true if both individual statements are true. It's the only way you get an and statement to be true. Okay? Let's do another one. Disjunctions. Disjunctions are or statements. And or statements are true if either of the individual statements themselves are true. You don't need both of them. You could have both of them, but you don't need both of them. And we're going to set up that same type of truth table. We've got column for P, column for Q, and I've got a column for P. I didn't tell you how it's written. It's a V. So just flip the V that was upside down, right side up. P or Q. Now, the P column and the Q column are exactly like they were before. I have, whoops, true, true, false, false, and then true, false, true, false. We're using our exact same people we just used. So I walk in. I was the first person, remember? Or maybe we have Dr. Marsh walk in. If you've had Dr. Marsh, that'll work as well. And we walk in and we say, I'm a woman and I teach math. I'm sorry, I meant to say or. I'm a woman or I teach math. That's true. It sounds funny to put the word or in there because both pieces are true, but by default, it's true. Then we have Dr. Young walk in, and Dr. Young says, I am a woman or I teach math. Still true, at least because she has one of the two components true. Not both, but that's not, she doesn't need that for an or statement. She just needs one of them. And then Dr. Bond walks in and he says, I'm a woman or I teach math. Also true, because he's got the math component that's going to be going for him on that one, right? And then Dr. Whitlock walks in and he says, I'm a woman or I teach math. It's false, because both of the individual pieces fail to be true. And that's for a disjunction. Okay, every time I get to this point, I think, I don't know why this isn't in here, but it isn't, so we're going to actually put it in here. No, I didn't. Maybe I got it put in here later. I think I did. I got it in here later. Okay, we're going to keep going. I used to not have the if-then parts here, but we'll do the if-then later. All right, so what we're going to do next is we're going to create a truth table for an arbitrary P and Q we don't have statements associated with, and we're just practicing putting our T's and F's in the right place. That's all we're doing on this problem, is practicing our arrangement of T's and F's. So as we're looking at this, again, just like I've told you before, you know the first two columns. They're P and Q, and they're T's and F's. Two trues, two falses, and then alternate true, false, true, false. The next thing to do is to take a look at what your actual individual statements are over here. One of them says P. We've got that one in our truth table. The other one says tilde Q. We do not have that in our truth table yet. But can we put it in there? Why, sure we can. We can. All we need to do is to come over here and now have a column that says tilde Q. How will I create my tilde Q column?
Whatever's P and not Q. Oh wait.
You're ahead of me. We've got that column coming up. Before then, we need a column for tilde Q.
Whatever it has to be the opposite of your original statement.
Yes. So, and the way that we get that without knowing original statements, because we weren't actually given that information, is we take the column Q, and what do we do to create the tilde Q column? Opposite. We flip it. We reverse it. Whatever was a T is now an F. Whatever was an F is now a T. So in my tilde Q column, I have false, true, false, true. Feels a little bit like you're just playing with T's and F's. Yeah. And it does for this problem, because that's what we're doing. We're practicing. Our last column was the one that Hannah was trying to give me information about. It's the and statement. It's the actual full statement that we're given in the problem. P and tilde Q. And we're comparing two columns. Which two columns? P and not Q, or tilde Q, or the opposite of Q, negation of Q. Those two columns. So the one that's written in the middle, it's part of my truth table, but I don't need to be concerned with it right now. It's not a part of the point of this problem where I am. I used it to create what I needed to create, and I'm done with it now. So comparing these two now, is this an and statement or an or statement? It's and. And when is an and statement true? When they're both true. So on the first row, I have true, I have false. Is that statement true then, or is it false? It's false, because they're not both true. The second row, I have a true statement on P, and I have a true statement on tilde Q. That will result in a true statement. The third row, I have false, false, which is a false statement. And on the fourth row, I have false, true, which is a false statement. Okay, we're not being asked to do anything with this. We're just getting practice at getting the T's and the F's in the right locations for this one. All right. Now, if we were comparing two statements and trying to decide if they meant the same thing, we would be looking to decide if something was what we call logically equivalent. And you've heard people do stuff like this before when they put lots of nots inside of a statement. They say, it is not true that I do not want to go to swim today. And you're like, wait a minute, you just said not twice. So do you want to swim or do you not want to swim? You know what I'm talking about, right? You start putting too many negations in, and you start having to try and figure out what was that they actually said. So logically equivalent statements are simply two statements that have the same truth value in every possible situation. And logically equivalent are written like this. It's P, and then you've got three lines, kind of like an equal sign, but with three of them, and then a Q. It means that these two statements are logically equivalent. So I'm going to give you an example of one that people use interchangeably that are not logically equivalent. Have you heard somebody say before, I couldn't care less? And you've also heard people say before, I could care less. And usually, no matter which one of those that they're talking about, they actually meant the same thing. But obviously they didn't, because there's the word not in one of them and it wasn't in the other one, correct? Those two statements would not be logically equivalent. But people meant them to be, because they said it quickly or they'd heard it said a number of times or whatever, right? So De Morgan's laws below are examples of this. These are actually supposed to be triple inequalities between them. I just don't have a button that allows me to do that. So let's just analyze the structure here, and then we'll pick up on talking about these some more tomorrow and how, or not tomorrow, but Friday, and more about how De Morgan's laws work. So on the first one, you see a tilde on the outside of parentheses, and inside the parentheses it says P and Q. And then on the right-hand side of that, you see a tilde applied to the P, the and became an or, and a tilde applied to the Q. And you have almost exactly the same thing in the second situation. You have a tilde on the outside, you have P or Q, and then the tilde is applied to the P, the tilde is applied to the Q, and the or changes to an and. So structurally, it almost feels like what happens when we do distribution with negatives. The negative applies to the two statements, where we create negations of them, but it also changes the ors to ands and ands to ors. Usually when students make a mistake, it's the and or they forget to change. The negations usually work themselves out okay. It's the and or that's forgotten. So we will pick up on how to actually do this with our language next time.